Electrons are very mobile. They can move from atom to atom. When they are exposed to energy, they go to an excited state where they jump to a higher energy level. They don't stay in this excited state forever. Immediately, they fall back down to the ground state and they give off that energy that they just absorbed. Electrons can't go in between energy levels. Here we have energy level 1, it's the closest one to the nucleus, and then we just count out from the nucleus. Energy level 2, 3, and 4. N is the energy level, or it's the first quantum number or the principal quantum number. So when you go from an energy level 4 to energy level 1, this electron would fall back to this. Versus if we had energy level 7 going to 5, and this didn't count out, we might see a red length of light come out of the 7 to 5, but we might see something like a blue light come out of the jump from 4 to 1. So which releases more energy? It's the 4 to 1 because it's a larger jump. And we also get a wavelength of light that has more energy. The energy levels in the atom, they're like steps in a ladder. Just as you climb a ladder rung by rung, and you don't hover in midair between rungs, it's the same thing for an electron. It jumps out in the successive orbitals of an atom. The more energy the electron has, the further away from the nucleus it will be. And the energy levels are not evenly spaced. So the first and second and third, they tend to be spaced a little bit further on. But then when you get up to the higher energy levels, they tend to be closer together. Those energy levels are quantized, meaning they're by steps. So it's not a continuous energy level where the electron can be anywhere outside the nucleus. Instead, you're going to find them at specific energy regions or quantized energy levels. This is Bohr's atomic model. He studied hydrogen, which has one proton and one electron. When you add one more electron, that goes into that first energy level, the n equals 1. But when we jump up to lithium, that first energy level can only have 2 electrons. So with lithium, we get a second energy level. And then going all the way to sodium, we can see that there are 2 electrons on the first energy level of sodium. And then the second energy level, the pattern is there's 8. And then we have sodium starting to put electrons on the third energy level. We can plot the energy given off by an atom using waves. When we're studying waves, we need to look at frequency and wavelength and speed. The frequency is this Greek letter nu. It's measured in hertz. 1 hertz is equal to 1 second, or sometimes you see an s to the minus 1. So the s is in the denominator. Frequency, what that means is if your eye was down here looking at this wavelength coming at you, you would count how many wavelengths go by per second, and that's known as the frequency. So how fast it's coming at you, the frequency, how many wavelengths per time. The wavelength would be from crest to crest. So from this to here, that's your wavelength. And that is measured with the Greek letter lambda. And it's measured in meters if we're talking about something like radio waves. But once we get to like visible light or microwaves, sometimes it's changed to nanometers. And this is the conversion to nanometers. Light travels at the speed of light, and this is a constant. So c is the speed of light. And amplitude, if you're looking at a certain wavelength that it is going up higher right here, that would be known as the amplitude. So this one versus this one, we can see that the amplitude is a lot more in the one I drew. So the amplitude represents how bright that photon that comes out of the atom is. So if we have a lot of atoms that are getting excited and then dropping back down in a certain wavelength, then that wavelength will be really bright because there's a lot of atoms that again are getting excited and then dropping back down. This is a formula in your data sheet. Its speed of light is equal to the wavelength times the frequency. The speed of light is always this number, 3 times 10 to the 8th. Therefore, if my wavelength goes up or gets longer, then my frequency will go down. So this is an indirect relationship. We can rearrange that equation. So if we needed to solve for wavelength, I could divide each side by frequency. So I would get wavelength equals the speed of light divided by frequency. And I also could use this equation to solve for the frequency. So I'd have frequency equals speed of light divided by the wavelength. Let's just do a sample problem. If a wavelength of light has a wavelength of 650 nanometers, what is the frequency? So I'm going to use this equation that I just did. I just rearranged it. The speed of light divided by 650 nanometers. And notice I wrote my units. This is going to prevent errors. Notice this is in nanometers and this is in meters, and so you can't cancel it. So I'm going to change nanometers by crossing out nanometers, and I'm just going to tack on a times 10 to the minus 9, and then that would give me my meters. When I do my math, I get 4.62 times 10 to the 14th, 1 over s, or you'd also see it as an s to the minus 1. So this is the frequency. So this is how many wavelengths are going by in the second. So a very large number. The light that comes out of the atom when it goes from a excited state to a ground state is also described as a photon or a quantum. This is just a packet of energy. So let's look at our energy equation. So this is also in your data sheet. Energy equals H. This is Planck's constant times the little v, which is our frequency. So Planck's constant is this really, really tiny number right here. And again, that's on your data sheet. This second value of Planck's constant, we will talk about later on in the year. And then recall that frequency is that its units is 1 over s. So this is the electromagnetic spectrum. There is a video right here that I do want you to see, so that should be also in with this video. There should be a link. On this electromagnetic spectrum, I want you to identify high energy, low energy, short wavelength, long wavelength, low frequency, high frequency. Let's start with the first one, high versus low energy. So we have gamma rays on one end and radio waves on the other. And I always remember this way. Which one will kill you? Well, not the radio waves. This one has low energy. And my gamma rays, this is a result of like a nuclear reaction. So this would have high energy. Next, short wavelength, long wavelength. So I can see my wavelength right here. So radio wavelengths are long, and these ones over here are short. And then let's look at frequency. So frequency, here's my numbers right there. So I have high frequency and low frequency. So let's look at a direct relationship. So that would mean if one goes up, the other one goes up. If one goes down, the other one goes down. And I can see I have low frequency and low energy. So those are a direct relationship. And then my inverse relationship, I see that I have a low frequency and a long wavelength. So those are opposite. And we've already mentioned these before. We also have energy could be put in there too. So energy and wavelength are also inverse. So where one goes up, the other one goes down. Visible light is right here. So you can see that we have low energy here and high energy here. This is just more information with the visible light spectrum that we can see. We can see just a small amount of it. But again, red wavelength, it's a longer wavelength, so it has less energy. So we can apply that to Star Wars. So we have a red lightsaber with Darth Vader and a blue lightsaber with Obi-Wan. Which lightsaber has the most energy? And it would be Obi-Wan. So this one's a lot higher energy. And so he should have won. So he truly sacrificed himself. Let's do a problem that combines both our equations here. And there is a way to combine the equations. So you just have one equation, but I always just do it separately. So this says a photon of light has a wavelength of 550 nanometers. Find the frequency and the energy. What color is the light? So that I can answer right now. I just look right here and I see that it's green. So 550 nanometers is green. We need to find the frequency and the energy, and let's go ahead and do that. So we're going to start off with our speed of light equation and find the frequency. So I have frequency is the speed of light divided by the wavelength. And don't forget, there's nanometers and meters, they don't match. So I'm going to cross this one out and just tack on times 10 to the minus 9. It's not written in the scientific notation. If it were, it would be 5.50 times 10 to the minus 7. But that's just a quick fix, so I just leave it as the 550. So there's my frequency. Now I'm going to put that into my energy equation. So here's Planck's constant, and there's the frequency I just found, and I get 3.616. I'm going to carry extra digit times 10 to the minus 9 joules. Okay, so there's my energy. Now that's for one photon, or for one little particle of light. The AP board loves to ask this question: what is the energy in kilojoules per mole? They like that unit. So notice my units are in joules now. To get to kilojoules, I'm going to divide by 1,000. Divide by 1,000. So that's going to give me 3.616 times 10 to the minus 22. And then I'm going to set up a little ratio. So this is how many kilojoules for one particle. Well, what if I have a whole mole? Well, I know that 6.02 times 10 to the 23rd particles equals 1 mole. So particles cancels, and I get as my final answer 217.7 or 218 kilojoules per mole. That's if we started with 3 sig figs. So maybe put a little dot right here. So it's 550 exactly. It gives us 3 sig figs. But this is how you use both the equations, and then you also change your joules to kilojoules per mole. So these are the steps you would take. If you got the last slide, go ahead and skip this one. This is just showing how we go from one particle to kilojoules per particle. So this one says, here's my frequency. So this one we're starting with frequency, and it says find the energy in kilojoules per mole. So here's my energy formula. I have Planck's constant here times my frequency. Seconds is going to cancel, and I just have to do my math. So again, this is for one particle, and then I'm just going to change it from joules to kilojoules. You can do that by 1,000 joules is equal to 1 kilojoule. So just move your decimal over so that number gets even smaller, and that's how many kilojoules. And then this is for one particle or one photon. Maybe I'll call it 1 photon this time. 1 photon is equal to 6.02 times 10 to the 23rd photons in 1 mole. And doing my math, I get 1.99 times 10 to the minus 8 kilojoules per mole. All right, so notice I always write my units because my units kind of guide me. So I can see I'm in joules, so then I know I have to go to kilojoules. And then I know that's kilojoules for 1 photon, so then I want to have a mole of photons. So I just let my units guide me. So Einstein, he was doing his research right around the time that they were discovering the parts of an atom, and he got the Nobel Prize for his photoelectric effect. And this is related to what we're talking about, electrons in the atom, how they can become excited. So what Einstein noticed is that if he shone certain wavelengths of light on a piece of metal, then these atoms would come off the metal. And he noticed that some wavelengths didn't work. Like for this piece of potassium, a wavelength of light isn't going to do anything. But look, green and blue will. And it is very specific towards the metal. So maybe I have like a blue-green light that comes in, and maybe nothing happens. So it's very, very specific. However, you can see that a lower energy wavelength like red doesn't do anything. It requires higher energy, but it is metal specific. And that's because every element has its own elemental fingerprint for how its electrons become excited and how those electrons drop back down to their ground states. If I have white light and I put through a prism, I get a rainbow. But if I take light and I shine it on an element, certain wavelengths will excite its electrons, and then of course it will drop back down to the ground state and have what's called an emission spectrum. And you can use this emission spectrum kind of like a fingerprint for person, can identify the person. Well, what bands of light are emitted from exciting electrons can help identify what element you have. So at the top here we have hydrogen. We see a red band, we see a blue-green band, and then we see blue and violet. And look at the next one, sodium, completely different. It has a pretty strong yellow band right there. And you see helium is even more different. So a different wavelength of red than what hydrogen has. And neon lights, they're kind of reddish, orangish, and you can see because of their emission spectrum, that's why they're in that reddish, orangish color. And then here's mercury. This is what we see in our fluorescent lights. This is kind of the pattern that we see in fluorescent lighting. If we have really, really bright wavelengths, then that is telling us that there's a lot of electrons that are becoming excited and then drop back down in that wavelength. If I have a mixture, the mixture will be made up of the individual elements. And in order for an element to be in the mixture, it needs to have all the wavelengths. So hydrogen has this band, this one, and these two. They're kind of faint. I have a hard time seeing them. But they need to match up in the mixture. If they're missing from the mixture, then we do not have that element. Even if just one band is missing, we don't have that element in the mixture. So there's a mixture down here. Go ahead and stop the video and figure out which ones are in the spectrum, which ones aren't. Okay, we're back now. I can see that barium is not in the mixture because you see how that one band is missing, and there might be others, but that's the one that stands out to me. So I know that barium's not in there. And some of these you might need a ruler to try to figure out. I'm not sure that this one is there. I probably have to have a ruler just to double check. But it seems like that one's off a little bit. So maybe that one's not there. You just want to make sure that they all line up. What is there? I think krypton matches up. We have all of those. And those two. This one, and there's a faint one that's right there. And so because it has all of the lines, then you would find krypton in there. And there's other ones in there too. You might have come up with some different ideas. In 1913, this is when Bohr did his Bohr model, and we found those electrons at specific regions from the nucleus. And Bohr was the one that he studied these emission spectra. So the emission spectra, it tells what was released, and before the emission spectrum was the absorption spectra. So what this means is that we can see that this element, it absorbed certain wavelengths, just like Einstein's photoelectric effect. Only certain wavelengths would liberate those electrons. Only certain wavelengths would the atom absorb, and then you can see kind of the second step, it emits them, and that's called an emission spectrum. So the continuous spectrum is just white light. That's all the wavelengths, but then you can see in this number 1, these are the wavelengths that the atom absorbs, and then it will emit the same wavelengths. So using these spectra, we can see out into space what elements are on our sun or what is in a distant star cluster. It's because of the spectra that comes to our eyes, and we are able to figure out what elements are in this ball of gas way far away. Here's just some more pictures of hydrogen and helium spectra. So again, it absorbs the light first, and then it emits it. So there's your emission spectra. So we can put this in tandem with the Bohr model. So we see that when there's a blue wavelength of light here, that means that it dropped back down and emitted that light, and it dropped quite far. So this one says it drops from a 5 to a 2. So that's energy level. And then we have this next one, this next light blue one. That one drops from a 4 to a 2. And then we have this red over here. It drops from a 3 to a 2. So again, it absorbs when it gets to a higher energy level, but then it emits or releases that energy in the form of light when it drops back down to its ground state. So Bohr was able to take all this spectra information and he was able to figure out those energy levels that go around an atom. Okay, when we heat up our sample or when we bombard a sample with visible light, this is the change that happens. We end up exciting valence electrons. What would happen if we had higher amounts of electromagnetic radiation? What if we use X-rays? Well, that would completely remove the electrons. It would remove valence electrons and it would remove core electrons. And we'll talk about valence and core in this unit. What if we have a very, very low amount of energy, like in the infrared area of the magnetic spectrum? Well, this just causes bonds to vibrate and to bend and to wag, is kind of how it's described. And what about those microwaves that you use to heat up your soup? Well, microwaves is a very low amount of electromagnetic radiation, and what it does is it causes the molecule to rotate. Here's just another picture of this. So again, we're going from high energy to low energy over here, and we can mess with the electrons in the atom. If it's a high amount of energy, we can knock the electrons completely off. So ultraviolet or in the visible spectrum, then we can excite electrons. If it's in the infrared, so past red and our eyes can't see it, what we do is it vibrates the molecules. Microwaves rotate the molecules around. So here's another picture of microwave molecular rotation. So as that microwave goes through your soup, it will cause the water molecules to flip. And when they flip, or rotate, they cause friction, and that will heats your food up. So I always remember microwaves usually have a plate that rotates. So microwaves rotate molecules such as water. And there's two pictures of it. You can see it just flipping and rotating around. Vibrational rotation. So this is the infrared area. So we have stretching of bonds right here. So there's different ways to stretch. They can stretch together or asymmetrical, or they can wag like they're waving up and down. All right, when we look at the Bohr model, we find that he was right on for hydrogen, but if we applied any other element, then we found that his model didn't work. So it didn't work for multi-electron atoms. So we need to come up with a new model. Along this time was Heisenberg, and he came up with his uncertainty principle. And in his research, he found that to know the exact path of the electron, you need to know the location and the momentum or the speed. And he discovered that when he was trying to figure out the location of the electron, then that would change the momentum. And when he was trying to figure out the momentum, that would change the location. And so he found by measuring one, you change the other. And so this is his uncertainty principle, that the more you know about the location of the electron, therefore the less you know about the momentum, and vice versa. So because of this, he said that Bohr model did not work because you can't know the path of an electron. You have to know both the location and momentum to be able to see an atom that has electrons going around the nucleus like planets go around the sun. And so the Bohr model that we use a lot in chemistry, it is incorrect. So we've looked at several models that have all been disproven. The last one here that we talked about today is the Bohr model, again with these orbitals. And now we're going to talk about this quantum mechanical model, or it's the electron cloud model. And it builds upon Bohr's model. With the invention of the supercomputer, this allowed Schrodinger to put all the information together, and he came up with this very complicated equation here, but I have it here to show you the x, y, and z. So this is coordinates. So he's able to figure out the probability of finding that electron any one place around the nucleus, and he came up with something that looked like this. So we see that there is a high probability, 90% probability of finding that first electron 53 picometers away from the nucleus. So what Schrodinger did was he used math to find the probability of where you would find that electron. And it matched up with Bohr's orbit models, where there's only certain orbits where you would find, or energy levels where you would find those electrons. And so this is the probability region that Schrodinger saw when he did his quantum mechanics. So this is the quantum mechanical model of the atom. So we have a very, very dense atomic nucleus. And I really think it should just be one little dot right there, but they made it a little bit bigger. And then we have a probability density of where that electron would be found a certain distance away from the nucleus. So, and I just drew a solid line, but it's not a solid line. This is your 90% line. So electrons are described as being found in clouds because of this fuzzy probability area. Orbitals or probability clouds don't have to be spherical. So we have an s orbital right here. So imagine it's a sphere. And again, you have that 90% probability of finding it that distance away from the nucleus. But you also have some different probability clouds. These ones are dumbbell shaped. These are p orbitals. And so in each of these electron clouds, you can find one or two electrons. And here's some other ones. These ones are called d orbitals. So it's more of like a clover leaf. And this one with the little donut, it's a little bit different. And then here's my f orbitals. So again, these are the probability clouds of where you would find one or two electrons. And in the atom, they all stack up on top of each other. The first energy level, you only have an s electron. The second energy level, you have an s electron, and you also have 3 p orbitals. The third energy level, it gets even more complicated. You have an s, you have 3 p's, and you also have some d's in there. So it gets really, really complicated for what it looks like. Here's kind of putting them all together so you can kind of visualize. But this is the model of the atom that we study today.